Good afternoon. Our capstone is titled AI-Assisted Airworthiness Requirements Traceability for Military UAS. I'm Bree Stewart, the Program Manager. Presenting with me are Jesse Smith, our Technical Point of Contact, and Amanda Johnson, who owns the airworthiness documentation and regulatory side. Over the next 15 minutes, we'll walk you through the problem we set out to solve, the methodology we built, the results we measured, and what we think matters most, why this is a contribution to engineering governance, not just another AI demonstration. Here's the problem. Every military aircraft that wants a flight release has to demonstrate compliance against airworthiness criteria. But those criteria aren't in one place. They're spread across documents written in silos. Department of Defense policy at the top, and then separate Air Force, Army, and Navy frameworks underneath. Today, an engineer reads each of those sources by hand, decides what applies, and builds a compliance matrix from scratch. And they do that again on every new program. The result is a process that's slow, that two engineers will do differently, and that no one can independently reconstruct afterwards. For a certification workflow, that last part, not being able to reconstruct it, is the real problem. So, here's our thesis, and it's a little counterintuitive. The goal is not to build an AI that finds the requirements correctly. Chasing accuracy is a moving target, and honestly, it doesn't help a certifier very much. Instead, we treat reproducibility as an engineering objective. The same inputs should reliably produce the same catalog and surface from same conflicts every single time. When you can agree that, the certifier's job changes. They stop rebuilding the analysis from scratch and start verifying a stable artifact by sampling it. That shift is the whole idea. Quickly, here's our roadmap. I've covered the problem and the thesis. Jesse will take you through the pipeline, how we proved it, repeats, and our dedication results. Then Amanda will cover the regulatory fit, what's genuinely novel here, and where the honest boundaries are. Jesse, over to you.
Thanks, Bree. I'm Jesse Smith, and I'll walk through how the pipeline actually works, and then we'll provide the reproducibility claim that Bree just described. This is the whole system on one slide. It's a 5-stage pipeline built as a Rust workspace. The single most important idea is the split you see here. The language model does the heavy lifting, reading and interpreting the text, while the framework around it does the heavy verification lifting. The model is treated as a black box behind the standard endpoint. Everything that makes the output trustworthy happens in the framework, not the model. Let me take the stages in turn. For the corporates, we use 16 publicly available U.S. military airworthiness documents. A document only got in if it was distributed through official channels with a stable URL and a pinned version. That emission rule matters, and Amanda will come back to why. Then the structure breaks those documents into citable segments. 5 parser families handle the different numbering conventions across the corpus. This stage is fully deterministic, no model involved. The same PDF always produces the same 802 segments. Now the model comes in for extraction. We're using IBM Granite. Every call is locked, temperature 0, top P1, fixed seed, and pinned context length. One careful point. We say that the generation layer is reproducible, not deterministic. Bitwise determinism isn't something a vendor guaranteed, so rather than assume it, we measured it. The context length settings, max model length is a load bearing. Change it and the output changes, so we pinned it and recorded it. Every record gets a stamp with a model fingerprint for the audit trail. So after extraction, everything has to pass 4 sequential gates before it's allowed in the catalog. Gate 1, the criteria has to resolve to a real ingested paragraph. Gate 2, if more than 8 words run verbatim from the source, it's rejected. Gate 3, a second model pass checks if the paraphrase is actually supported by the cited text. And Gate 4 removes duplicates. You can see the effect of the funnel of roughly 4,900 candidate concepts. 2,412 were accepted, and nearly 2,500 were rejected. Each rejection is logged with a reason. The pipeline would rather stay silent and surface something that it can't ground in reality. This is the primary claim, and this is the evidence for it. Most AI papers write temperature equals 0 and move on. We ran the same interface 500 times and hashed every single output. All 500 produced one identical hash. That's what makes everything else meaningful. A reviewer who reruns the pipeline at our pinned commit gets exactly the same catalog and the same findings. That's the property that turns certification review from re-derivation into sampling. Now, a design decision I want to highlight because it's backed by human factors research. When you show an engineer a confidence score 92%, the research says they defer to it and stop judging independently. That automation bias and cautionary labels don't fix it. So we made a deliberate choice. The self-assessment, its confidence, its own labels, is preserved internally for audit, but we never reaches the viewer's screen. What the reviewer sees is the primary evidence, the citation, the source text, the paraphrase, and the reasoning about the source itself. We're strengthening the human judgment by withholding a number, not weakening it. We evaluated against a seeded fictional program with a sealed answer key. Track 1 is the requirements layer. Against 13 scoreable conflicts, we scored 10 strong, 3 partials, and a number I care about, 0 misses. Both of the hardest planet conflicts were caught. A cross requirement contradiction where 2 reasonable requirements can't both be satisfied came out strong. And a physics level infeasibility, a loitering requirement that can't come close to the platform's max ceiling, came out partial. The pipeline flagged attention, even though the humans still supplied the energy density arguments. Nothing we seeded escaped entirely. Track 2 is the evidence layer. Verification reports for gaps. Here we caught 8 of 14 planet gaps, including the crown jewel, a software design insurance gap hidden behind maturity claim. Here our honest limitation is stated plainly. On 2 completely clean reports, the pipeline overflagged. 14 false reports. Tuning that is future work. But notice how the earlier design decisions contain it. Because no confidence score rides along with the finding, an overflag just costs the reviewer some time. It never writes false confidence into the compliance record. Now I'll turn it over to Amanda.
Thank you, Jesse. I'm Amanda, and I'll cover why the public corpus choice matters, how the methodology lines up with the regulatory landscape, and what we think is genuinely new. Jesse mentioned our admission rule, public sources only. Here's why that's foundational. Most published traceability tools rely on civil regulations or proprietary program data, and in the military space, ITAR and restricted distribution rules fragment the field. If your corpus isn't public, no one outside can reproduce or check your results. So we restricted ourselves to version pinned, publicly distributed government documents, the anchors you see here, from DoD 15030.61 through the service instructions. Any researcher can rebuild our exact source set from the inventory. That reconstructability is the precondition for an auditable claim. It's what lets reproducibility mean anything. We also designed the methodology to fit the emerging AI assurance landscape. I want to be precise. We are not claiming qualification against any of these. We're showing that the architecture is built so a future qualification effort has a real starting point. ESA's draft AI specification expects a human in the loop with audit-only self-assessment. That's our ADR 0012. DO 330, the tool qualification standard, needs determinism and traceability. That's our locked parameter contract and versioned records. The FAA roadmap and the DoD responsible AI strategy both ask for inspectable, traceable, governable behavior. Every one of these frames cares about repeatability over raw correctness, which is exactly the property we engineered. So, what's the actual contribution? It's not the specific model or the language it's written in. or even the military domain. Those are implementation choices we could swap out. The durable contribution is the governance architecture as a whole. Locked interference, a version pinned corpus, paragraph level citations, structural validation gates, audit only AI self assessment, and a corpus agnostic design. It's that combination that's let a language model sit inside a certification workflow while producing output that's verified rather than trusted. And because it's corpus agnostic, the same pattern transfers to civil airworthiness or any regulated engineering domain. Before we close, our honest boundaries. We overflagged clean evidence inputs. The live query surface used simple retrieval at our pinned commit. The civil extension is designed, but not yet validated. We evaluated on a realistic fictional program, not a real certification package, and we claim no compliance qualification. Future work follows directly from those: wiring live retrieval fully, tuning precision, checklist style prompting to catch gaps phrased as omissions, validating the civil corpus, and exploring embedding or graph based retrieval. None of these are hidden, surfacing them is part of the discipline. To conclude, we set out to make AI assisted traceability trustworthy for certification work. Not by making the model more correct, but by making the pipeline reproducible and every claim verifiable. 500 runs passed, 2,400 concepts, each resolving to a public paragraph, 0 misses across 13 seeded conflicts. What we're really offering is a documented pattern for putting a language model inside a certification workflow without handing it decision authority. Thank you from all three of us. We're happy to take your questions now.